Okay. Samuel, you mentioned improving agents in this chapter. What are the key advancements?
Yeah, we're building on previous chapters. Two main improvements. First, we're using A-return for policy evaluation.
A-return? Explain that for us.
It's a way to estimate the value of an action. It's more efficient than standard methods. Think of it like speeding up the learning process. It helps the agent get to the right answer quicker.
So, it's faster learning?
Exactly. And we're using it for both on-policy and off-policy methods.
On-policy and off-policy? What's the difference?
On-policy means the agent learns while following a policy. Off-policy means the agent learns by sampling actions outside the current policy. In essence, on-policy is about refining what it's already doing, and off-policy is like trying different approaches to see what works better.
Makes sense. What's the second improvement?
Model-based reinforcement learning. Instead of just learning by trial and error, these agents try to create a model of the environment.
Like a map?
Exactly, a map of the environment. So they understand how actions affect the environment.
That sounds powerful. How does this help?
It often leads to faster learning and achieving optimal results. You get more out of the data.
So, they're learning not just the best action, but the whole system?
They're learning the environment structure. That gives them a better understanding.
Fascinating. So, model-based methods, instead of blindly testing everything, they try to learn a model?
Precisely. And they use this model to plan, in essence.
So, you can combine these improvements.
Absolutely. You can use the A-return with a model-based approach. It's a powerful combo for faster learning and optimal solutions.
Excellent. That's a helpful summary of the key advancements. Thanks, Samuel. So, SARSA is basically an upgrade to SARSA, right?
Yeah, exactly. It's a small tweak, but it makes a big difference.
How does it improve upon SARSA?
Instead of using a one-step estimate, SARSA A uses the A-return.
A-return? What's that?
It's like a more complete picture of the future reward.
Okay. Can you give an example?
Imagine a game. SARSA might look just one step ahead, whereas SARSA A factors in potential rewards from several steps down the line.
So, it's more far-sighted. Makes sense. You also mentioned eligibility traces. What are those?
Eligibility traces keep track of past states or state action pairs.
Why are they important?
They help the algorithm learn from its past actions and understand which states and actions led to rewards. Think of it like remembering which moves worked well and which didn't.
So, there are different types of eligibility traces?
Yeah, accumulating traces and replacing traces. Accumulating traces, well, they just keep adding up.
So, they just keep growing?
Potentially. And that's a key difference between the two. Replacing traces clip eligibility to a maximum value, preventing them from becoming too large.
That sounds crucial. Why is that important? What could go wrong if they keep growing?
If they grow without bound, the algorithm can get lost in noise. Imagine a loop in the game. Without replacing, it'd keep assigning more importance to this loop. Replacing helps correct these issues.
So, replacing traces are more stable?
Absolutely. They prevent the agent from getting stuck in infinite loops.
And the history you mentioned, was that important for understanding the algorithm's origin?
Yeah, definitely. Understanding the origin sheds light on the reasoning behind the names and the development path of this algorithm, like how it evolved from a modified version.
Thanks, Samuel. That's super helpful. So, Samuel, you've described accumulating traces. Can you explain how they work in reinforcement learning?
Accumulating traces keep track of how often and recently an agent interacts with a state action pair. It's a way to combine frequency and recency.
So, if an agent repeatedly tries a state action pair, the trace grows?
Exactly. The trace value goes up each time, unlike replacing traces, which only have a maximum value of 1. This means accumulating traces can reward a frequent state action pair more heavily.
Why might that be important?
Imagine a loop in a game. Repeatedly doing a state action pair in that loop is critical. If we don't account for frequency, our model might undervalue that sequence. The accumulating trace captures the importance of that loop.
And what about recency?
The trace also decays over time. So even if an action was very frequent in the past, it slowly becomes less important to the current state. It balances the frequency data, making it more relevant.
Your example about the kid's sleep, that's a really interesting analogy. How does that illustrate the difference?
Yeah. The gluten example shows how accumulating traces might lead you to focus too much on frequent events, lots of gluten. While bananas were rarer, but more recent and linked to the issue.
Okay, so replacing traces, as opposed to accumulating traces, seem to moderate the importance of frequent events.
Exactly. They prevent the model from overemphasizing past events.
So, in the replacing trace scenario, there's a trade-off between frequency and recency?
Absolutely. The replacing trace mechanism assigns a maximum of one eligibility. Thus, a more recent, less frequent action can still have a greater impact.
That makes sense. How does this affect the Q function update?
The accumulating trace allows the trace values to be above 1. This means that the effect of the TD error on the Q function is potentially larger for frequent/recent state action pairs.
That's a crucial detail. How does this compare to the code snippet you presented earlier?
The code snippets showcase how these mechanisms modify the update of the Q function based on how an agent interacts with the environment.
That's a really insightful explanation. It highlights the practical application of these concepts in reinforcement learning. Thanks, Samuel. So, Watkins's QA builds on Q-learning, right? Can you explain the core difference?
Yeah, it's a crucial extension. Q-learning, it's pretty straightforward. It directly learns the value of taking an action in a specific state.
Makes sense.
QA, though, it uses something called the A return. This adjusts policy evaluation. Instead of the standard TD target, it uses the A return for off-policy control.
So, what's the A return?
Essentially, it's a modified reward signal, taking into account actions not directly from the current policy.
Gotcha. That's important for off-policy learning, I get it. So, you mentioned eligibility traces? How do they fit in?
There are different ways to incorporate eligibility traces into Q-learning. Watkins's Q lambda is one approach. It's basically a way to give more weight to recently visited state action pairs when updating the Q values.
So, it's like a memory?
Exactly. It remembers previous interactions to adjust learning. It's crucial for situations with delayed rewards. Think about games. Often, the reward comes much later, and eligibility traces help the algorithm learn more effectively from these situations.
Makes sense. What's the historical context here?
Q-learning was a significant step. Watkins laid a solid foundation. The algorithm is still used today because it's simple and performs well.
So, are there any potential downsides to this?
Well, one thing is the off-policy aspect. Being off-policy, it learns from actions not dictated by the current policy. You gotta be careful when you use that because it can sometimes lead to instability in the learning process, especially in complex environments.
Right, makes sense. You also mentioned Watkins's Q lambda and Peng's Q lambda. What's the difference?
There's a slight difference in the way they use eligibility traces. Watkins's original method is more straightforward, but Peng's version has adjustments for certain kinds of situations.
Okay, interesting. What about this Python code you showed? Can you explain it?
Sure. The code you're showing essentially implements the Watkins's Q lambda method. It initializes a Q table and eligibility traces, along with essential variables like learning rates and exploration rates. It then uses a loop to interact with the environment, collect rewards, and update the Q values based on the eligibility traces and the TD error.
So, what are the practical implications?
Imagine training an agent to play a complex game. Watkins's Q lambda method helps the agent learn effectively from potentially delayed rewards, by allowing the agent to remember past interactions. This is key for situations with non-immediate rewards, like in many board games or robotics tasks.
Sounds very cool. Thanks, Samuel. This is great. So, Samuel, you mentioned model-free reinforcement learning doesn't need a predefined model. That's cool, but what are the trade-offs?
Yeah, it's really powerful. Imagine learning to play Go, Alfred. A model of all possible moves, 10 to the 170th possible states, is practically impossible. Model-free methods learn without that.
But how does it actually learn if it doesn't know the rules?
It learns through trial and error, by interacting directly with the environment. It's like a kid learning to ride a bike. They fall down, get back up, and eventually figure it out. This direct experience is invaluable, especially in complex situations.
So, it's kind of like trial and error learning in the world of AI.
Precisely. It tries different actions, sees the results, and adjusts its strategy accordingly.
In model-based learning, it sounds like it's the opposite, right? It builds a model first.
Exactly. It tries to create a simplified map of the environment, like drawing a map in your head of a new city, then uses that map to figure out the best route.
So it learns the model from the data it's gathering.
Right. The agent figures out the probabilities of different actions and outcomes. That map helps it plan, and learning that model often takes fewer examples to reach optimal strategies. Think of the planning algorithms, like value iteration, as a sophisticated map-making process built into the learning algorithm itself.
So model-based is like pre-planning, and model-free is on the fly?
That's a good way to think about it. Model-free is reacting immediately to what happens. Model-based is strategically planning based on an internal map. It's like the difference between reacting to a surprise and meticulously studying a map before you head out.
But there are limitations, right?
Well, model-free methods can struggle with really complex environments because they need a lot of experience to find the optimal strategy. Model-based methods, though, can be quicker if you have a good map or model.
Interesting. Can you elaborate on those sampling models and distributional models?
Sampling models give you one possible future outcome of the environment. Imagine flipping a coin. You get either heads or tails, not the probability of heads or tails. Distributional models give you the full probability distribution, the chance of heads and the chance of tails. The latter is usually more informative, especially when dealing with uncertainty.
So, distributional models are more accurate then?
Generally, yes. They have more complete information. They give you a fuller understanding of the uncertainty involved in the environment's behavior.
So, Dyna-Q, this model-based reinforcement learning method, it sounds pretty cool. How does it combine planning and model-free learning?
Yeah, it's a powerful approach. Imagine you're training an AI to play a game. A model-free method, like Q-learning, just learns from experience. It's like trying every move in the game and seeing what works. Dyna-Q takes it further.
How does it do that?
It builds a model of the environment. It learns about how the game world reacts to your actions, storing probabilities of different outcomes. Then, it uses that model for planning. Planning is like running simulations, exploring different possible actions and figuring out what leads to the best results.
And this model, is it something like a mini-game within the AI itself?
Exactly. Think of it as a virtual reality experience within the AI. It's not the real world, but it's a representation of it. It lets the AI simulate actions and outcomes, improving the overall value function.
So, how does it keep track of all these interactions? Are there internal databases?
Dyna-Q uses tensors, which are basically multi-dimensional arrays, to store the transition probabilities. They keep a record of which states led to which others, and what rewards resulted. Another tensor stores average rewards for the same transitions. This lets it make educated guesses about what's likely to happen, even if the current game experience hasn't seen it.
Interesting. So, there's a learning phase?
Definitely. This process is reflected in the code snippet. It initializes these tensors with zeros, then updates them as it gets more game experience and learns from its model.
And the planning part? How does that work?
It picks states and actions that have been observed, essentially choosing the game scenarios it thinks might be most valuable. It uses the model to simulate those choices. Then, using the simulated experience, it refines the value function and policy.
How are those Q values updated? It's a little complex.
It updates Q values based on how well a particular state action pair led to better rewards in previous experiences or simulations. The updating process, the model improvement process, also adjusts based on the number of observed transitions, preventing random rewards from overwhelming the value function.
So, the planning portion is like simulation, learning through virtual experience?
Exactly. It uses the model to simulate different actions in similar situations.
What are the advantages of Dyna-Q over strictly model-free approaches?
It can learn faster in some cases because the model helps to improve exploration, making it more efficient. It can also generalize to new situations.
Are there any downsides?
Potentially, The model can become inaccurate if the environment changes or if the model is not regularly updated, resulting in flawed simulations. There's a fine balance between model learning and exploration of the real environment.
Right. So, it needs more real-world feedback to correct any inaccuracies in its internal models, correct?
Exactly. The model isn't perfect. It needs real-world data to correct for inaccuracies.
So, trajectory sampling, this new approach, it seems to prioritize learning from the immediate future. Makes sense, right?
Exactly. Instead of randomly picking states from our learned model, trajectory sampling focuses on likely upcoming states. Think of it like planning your week, not just some random point in the future.
Okay, but how does it actually work in practice? Can you give me a concrete example?
Sure. Let's say our agent's in a particular state. Trajectory sampling starts from that state. It then figures out the best actions based on its current knowledge, and follows a sequence of those actions. It does this for a set number of steps.
So, it's like a mini simulation?
Precisely. A simulated trajectory. It creates a sequence of states and rewards. The key is that it uses the policy learned thus far, helping the agent avoid getting sidetracked.
And how does that differ from Dyna-Q? It's also model-based, right?
Dyna-Q randomly samples from the model. Trajectory sampling, on the other hand, generates trajectories focusing on the agent's current state, the agent's immediate surroundings.
What about the code you showed us? The max_trajectory_depth variable. What does that do?
That limits the length of the simulated trajectories. The longer the trajectories, the more steps into the future.
Interesting. So, a balance between exploration and the immediate future?
Exactly. We don't want our trajectories to get so long that we lose focus on immediate rewards.
That makes sense. Do you see any potential downsides to this approach?
Well, it might not explore all possible state action pairs as thoroughly. Dyna-Q, with its random sampling, potentially gives the agent more general experience.
But if the model isn't complete, or our agent lacks knowledge of some states, wouldn't that potentially be problematic?
Potentially. The agent might miss valuable information if the simulation doesn't encompass certain state action transitions. That's why it's often beneficial to combine with other methods to get a more comprehensive understanding.
Excellent point. It seems like there's a balance to strike between the immediate future and the long-term possibilities. Trajectory sampling is a crucial tool in reinforcement learning.
Absolutely. It's a very effective technique for model-based RL. It's very beneficial for games where immediate reward is significant, and it tends to be quite stable.